All right. Hi, I'm Maddie Lucey. I'm a grad student at UT Austin. And yeah, I'm here to tell you about my work on the dynamics school about the interplay of orbits and potentials in our Milky Way's bar. So you've already heard a lot about bars this morning, but just reintroducing them and the way we kind of parameterize them in general. So we have length, mass, which is like how many stars, or you can also think about that as the strength of the bar. And then we have the pattern speed, which is how fast it's rotating. And luckily, we have a bar in our Milky Way, and this became evident in the early 90s. There's a lot of evidence leading up to this, but it became like the smoking gun was the when looking at the density of stars along different lines of sight, you can see different projections. So here I'm showing X and Y. So you're looking down on the plane and you can see L is like how you're looking at the bar, and B is so L is like looking towards the center of the galaxy, and B is up and down from the galactic plane. And so you can see that looking towards the center of galaxy, the star counts should be a function of your line of sight. And so that was like kind of the big evidence for our Milky Way's bar. And so now we have this awesome chance to study bars up close and in detail, because now we can resolve individual stars, that we have one in our own galaxy. But also the bar does change a lot of what we want to do in the Milky Way dynamics-wise. So in the halo, Sarah has shown that it really affects our stellar streams. So this is simulations of the PAL5 stream. And so you're looking at different on-sky simulations of it with different pattern speeds of a bar. And so you can see that really changes where the gap in the PAL5 stream is. So basically, if we want to use these gaps to figure out dark matter, we need to understand our bar, because they also affect the gaps in the streams. Also, we see the bar affecting things going on in the disk. So this is work from Jason. And so you can see that's our like local velocity structure in U and V. And so bars with different parameters lead to very different velocity structure in our solar neighborhood. And so there's kind of this debate going on about, is the bar 3.5 kiloparsecs long? It's like the short fast bar versus the long slow bar. And whichever model we actually have in our bar is going to really impact our local velocity structure. And so people have been trying to figure out and parameterize our bar. And so one way people do that is star counts as a function of the line of sight to parameterize the mass or strength of the bar, and also the bar length. And so here the black points are the actual star counts of red clump stars. And so since red clump stars are standard candles, this x-axis, which is the corrected magnitude, can actually be, just think of it as distance. So think of that x-axis as distance, and then you have star counts. The black points are the data. The lines of different colors are models for different, looking at different galactic latitudes, so in and out of the plane, and then the different galactic longitudes there. And so that's how we're trying to get at the mass and bar length. And then we also try to get at the pattern speed of the bar through kinematics. And so that is a bit easier to measure. And so we have kind of coming to a bit of a consensus of the bar's pattern speed being around 40 kilometers per second. And so it's really more of the bar mass and length that is still very uncertain these days. And so our question for our project is, can we constrain the length of the bar by looking at the last trapped orbit, or are we just going to get back the bar length of the potential we assume to calculate the orbits? So that's the goal of our work, is to answer these questions. And so what we're going to use is apogee and Gaia data. So you can see we're using the Astro and N different distances, if you're familiar with that. But here is just the projection of them in X and Y. And so the sun is marked as our star, the center of the galaxy, and the bar is marked there too. And so we're just going to take a quadrant where the bar is poking into as our data to calculate orbits with. But to do all this, we need to figure out what a bar star is in the first place. So here I'm showing basically, this is the same apogee star calculated in a potential without a bar and calculated in a potential with a bar. And so, yeah, the top row is in the co-rotating frame with the bar on the right. And so you can see the orbit more clearly. And so basically how we're going to define bar stars is from this flattening that we see along the bar direction in the co-rotating frame. So in the non-bar, you see that this X max and Y max are about equivalent. And so you get X max over Y max equals 1. You're not getting any elongation along the bar. And then in the bar orbit, you do see that Y max gets smushed. And so we have X max over Y max greater than 1. And so that's how we're going to select our bar stars. And so now we have 10,000 random apogee stars from that quadrant. We're integrating their orbits in GalPi using a Denon bar potential. And now we're looking at different X max and Y max cuts. What kind of apocenter, pericenter distributions does that lead to? And the points are colored by their Z max. And so over there, I'm just showing the kind of eccentricities we're looking at. They're not, obviously the orbits are not actually ellipses like that. They're doing all sorts of things, but just as an example of kind of how flattened we're looking at. And so you can see in 1.1 that there's stuff that's not even coming within 5 kiloparsecs of the center of the galaxy. And so that's not going to be our bar stuff. And so we are, with just 1.1, we are getting some disk contamination. But as we move down, we see that that goes away, the higher X max and Y max cuts. And then we also see this really interesting kind of bimodality in the apocenter distributions, which we definitely want to investigate and see, are these all actually bar stars? So now comes a really fun game that we're going to play called Do You Know What a Bar Star Is? Your new favorite game show. So how we're going to play is I'm going to do a region of this diagram and show some orbits of stars, and you are going to tell me whether or not it's a bar star. So let's just do the trial run real quick. So this star here, you can see X and Y projections, and then the Z there, and then the background I'm showing that Denon bar potential that we're using. And so raise your hand if you think this is a bar star. I think that's, most people say it's a bar star. Now you say it's not a bar star? All right, okay, what about this one? Is this a bar star? No? Wow, okay, well. Let's move our box over a little bit. Now, so we're looking at slightly larger apocenters and pericenters. Okay, is this a bar star? No, okay. What about this one? No, you got some strict definitions. All right. All right, moving out, okay. Now we're into this second peak of our distribution in apocenter. Is this a bar star? No, okay. What about this one? Well, yes. Is this a bar star? Is this a bar star? No, okay. Maybe? Some people? Okay, yes. We see some yeses on this one. All right, and now moving kind of farther out and also closer in pericenter. So we're getting some of these higher Z max yellow points that you see. Is this a bar star? Yes, maybe. Some yeses. Is this a bar star? No, yeah. What about this crazy one? Some people say yes. All right. So the point of this is that no one really knows what a bar star is. We all have very different definitions, but how we're going to define it is I'm going to fit a Gaussian mixture model to our distribution of apocenters for an X max Y max cut of 1.25. So I'm definitely not getting any of that weird disk stuff that didn't come within 5 kiloparsecs. But now, so the disk stuff, everything that doesn't match my X max Y max cut, I have in gray plotted here. And then the X max Y max cut stuff is in the blue, purpley color. And then I'm marking the mean of that inner distribution and the 3 sigma. And then this is, that black dashed line is actually co-rotation. So we're going to just count this inner distribution as our bar stars here, because the co-rotation stuff is a bit iffy, as we saw. So yeah, so we're treating our 3 sigma also as a kind of our last bar star, as the end of that distribution. Yeah. So now we can look at what happens when I change the pattern speed. How does my distribution change? And so how I'm going to kind of look at this, these are 2 different pattern speeds for here. So I've increased it on the left, and on the right, I've decreased it. And this is kind of increasing and decreasing by 20%. And it's kind of close to the high one is that short fast bar model, and the low, I mean, kind of that is more the long slow bar, but yeah, close to what the range of what we think the Milky Way might possibly have. And so what I'm going to do is just take the slowest point and plot it up there. So I have the mean in red and the 3 sigma line in green for the slowest pattern speed. And then the next one, the fiducial model, and then the highest pattern speed. So we can look at how the mean and the 3 sigma line changes as a function of our pattern speed to kind of see how our distribution is affected by the pattern speed. And then just co-rotation I've added here to also kind of guide our eye and see that, yes, it makes sense that the co-rotation is moving in as we're increasing our pattern speed. But what we see basically is that the pattern speed, the potential pattern speed, does not seem to affect the apocenter distribution of our bar stars. And so that's kind of our first result, is that just increasing the potential's pattern speed does not have much of an impact on the apocenter distribution of our bar stars. Okay, so next, now I'm changing the bar length. So the assumed potential's bar length is changing. And now what we see, which was a really surprising result, is that the apocenter distribution of our bar stars is again not changing. And so this was really surprising because we thought, oh, my potential's bar length should affect my actual bar's length. And so if we're defining this last bar star as our last trapped star, we're seeing that the potential length that we assume is not actually impacting the measured length that we're getting. Next, we're going to change the bar strength, so basically the mass of the bar. And so this AF is actually a measure of like the ratio of the radial force of the disc to the bar. And so increasing that AF is going to increase our bar strength, and decreasing it going to decrease bar strength. Okay, so we see this is what really impacts the apocenter distribution of our bar stars. So this was a bit of a surprising result too, but maybe we should have expected it. I don't know. We'll ask the theorists. Okay, so not only does the distribution change, but the number of stars change, so the strength of the distribution, but we see that that doesn't change much. And so here you can see how that changes with the pattern speed. So I've normalized this so that the fiducial model is at 1, so you're seeing kind of the percent change over time. And so that's with a higher pattern speed, we're decreasing the number of stars that we're trapping, which makes sense because the slower one is going to get closer to the disk and be able to trap more stars easily. So we see the pattern speeds decreasing the number of stars trapped as we increase. For the bar radius, what we see is there's an increase with a longer potential bar length for trapping more stars. That also kind of makes sense, but it's a very small change compared to the pattern speed. And then for the bar strength, we're seeing our biggest change. We're seeing that makes sense. The potential's bar strength. As you make it a lot stronger, we're going to trap more stars. All right, so again, we're seeing potential bar strength is really kind of determining what our stars are doing. But so going back to our question, we haven't really answered if we're going to be able to constrain it with the apogee data. But what we have learned is that we need to change our question to actually thinking about, does the bars, the potential strength that we assume is just going to give us our radius of our last trap bar instead of the length. Yeah. So we still need to see if the apogee data is actually constraining at all. So is this apogee data impacting our measurement of the apocenter of the last trap star, or is it just this bar strength? And so to do that, the next thing we're going to do is throw random test particles in and see if we get the same answer. And if not, that means that apogee data is actually telling us something. And then we're also going to test in a simulation about where we already know the true bar length to see if there's something about the way we're defining the last trap bar star with our X max, Y max cut, if that's giving us the answer to just make sure. Yeah. And thanks to everyone here, yeah.
Okay, so had you known what you know now that you wanted to change the question, what would have been like your different approach? So rather than just like, you've outlined here some of your next steps, but is there something you would have done differently, some different parameter that you would have started with to test if you had known you were going to look at bar strength rather than bar length? Or would you do the same tests?
I think I would do the same test, but I maybe would have started with the random test particles first, just because, yeah, it's hard to know if it's what's the apogee data is really affecting. Mm-hmm. Yeah.
I was wondering if you've looked at, the errors on the apogee data and the Gaia data. How does sort of accounting for them change your estimates of bar length? And is it? I mean, will you get the same? Would you think you'd get similar results for?
Yeah, that's a great question. We have not done any kind of uncertainty analysis yet. And so we can definitely like strap this in the future. But I would have to say, like with the 10,000 stars, like I feel like you're kind of averaging things out a little bit. So I don't know if much would change is what I'm saying. And we are using spectrophotometric distances, so they are a little bit better than just like Gaia parallaxes.
This is maybe a silly question, but how much does the fact that we know we're currently merging with other galaxies affect any of this? Because none of the models have those, right? They have a moving bar, but they don't have, SAG or the LMC.
Yeah, well, so you mean like my potentials that I'm assuming?
Yeah, like would you expect that to have a big effect or a small effect? Like, does that come in at all, or?
Yeah, I would not expect that to have much an effect at all, just because it really just comes down to the potential we're assuming, and so the potential in the center of the galaxy is not much affected by Sagittarius, to my knowledge.
Really nice talk, first off. Changing the bar strength and the bar length will also change the mass distribution, which will change the apocenters just because you've changed how the mass is distributed. So have you also checked to see if you just replace the bar, forget about something that's triaxial, just put put a different thing in that's spherical, does that change the epicenter distribution too?
Yeah, that's also definitely a next step, is because changing the halo mass overall. Yeah, is definitely also because I think it is probably just coming down to the mass distribution.
I have a question, but I have more of a comment, which is that I think, and this is all great, but one has to be careful that one doesn't think of the bar length or the bar potential and the bar orbits as independent, because they're not, right? It's the bar that's made out of orbits. So, I'd kind of like to take, your approach and then the modeling approach from yesterday and put them together. So an interesting thing might be to try and make, Schwarzschild orbits in the Denon potential and see what you need to do in order to get the orbit distribution that satisfies the Denon potential, and then compare that with your data. Is that consistent? Because then you have everything sort of adding up to a single coherent whole. I'm worried that you're giving yourself too many degrees of freedom.
Yeah, so that's definitely why we're going to go to simulations next and also do the random test particles. But it is, so if the random test particles do not trap stars out to 6 kiloparsecs, if I assume a bar length of 6 kiloparsecs, I feel like that would be telling us something maybe about bars, that the mass and the length are more correlated than maybe previously thought. Does that make sense to you? Can you just change these 2 parameters without changing the others?
No, you can't. I mean, I guess that's the point. I think you'd get a lot of insight from Schwarzschild modeling, because you put in the potential and you assume a pattern speed. There are orbits that you can't make, say, between 3 kiloparsecs and 6 kiloparsecs, even if you put your co-rotation at 6 kiloparsecs. A strong potential has this kind of no man's land of crazy resonant islands, and you can't make bar supporting stars there, so that you're going to be limited in where you can do that.
Be limited by the pattern speed?
By the pattern speed and the potential, but together. But primarily, it's going to be the pattern speed given a potential. It's going to make, for a strong enough, it depends on the amplitude. So to make a long story short, you're not going to be able to get your last trapped orbit in a strong potential go all the way out to co-rotation. It's just not going to happen.
Right.
So the two have to be sort of treated together. I guess that's my point.
Yeah.